Okay, well, good evening, everybody. It's 7 o'clock, and welcome to our latest webinar. This is Weather 101, which is kind of a basic look at what goes into weather, talk a little about climate. I'll show you some of the topics in a couple of minutes. Before we get started, just want to let everybody know everyone is on mute. We do this for all of our webinars to avoid background noise, but if you have a question, please use the chat box and we'll answer as many as we can at the end. All of our webinars, including this one, are recorded and are posted to our NWS Boston YouTube video page. That'll be done in a day or two, so you can find this there. Coming up, we have some different topics for webinars over the summer. So right now we have one on Thursday, July 2nd, talking about marine forecasting, and that's really for boaters. That's wind and wave forecasting, talking about things like ocean storms, hurricanes, rip currents. So if you have an interest in that, please join us. And then Tuesday, July 7th, this is a new webinar that was scheduled. This is Severe Weather 101, which will go over some of the basics of like thunderstorms, talk about some of the hazards like tornadoes, flash floods, hail, things like that. It's pretty basic. We don't get into too much detail. And then also coming up this summer, look for Tropical Weather 101, talking about tropical storms and hurricanes, and learn a little bit more about that as we get deeper into hurricane season. Also going to do a basic radar interpretation. If you like to look at radar data at home, this is probably for you. Again, very basic, but just shows you some things to look at when you're looking at radar data on your own. We're going to do a Climate 101, talk a little bit about the climate here in southern New England and some of the tools you can use to look at climate data on your own. This Weather 101 course will be followed by Weather 202. That's our next level, and that will go into a little bit more with forecasting. We may do kind of a live forecasting situation and show what's going on for the next few days and show you some of the tools that we use. We're also going to look at southern New England tornadoes. We've had quite a few of those over the past few years. We're also going to start a series called Memorable Southern New England Storms. If you've been on social media, you've probably seen our This Day in Weather History series, so this will kind of tie in with that. We'll probably go by decade and work our way from kind of the current decade backwards, and we have events back to the 1700s and even some 1600s from some weather journals. So we'll go into some of the more memorable storms of those eras. Also coming in the fall, look for Winter Weather 101. We know this one's going to be pretty popular, talking about winter weather, nor'easters, blizzards, all that good stuff that snow lovers rejoice at. And also probably do a short one on hazard simplification in the National Weather Service. We're looking at simplifying all of our watch warnings advisories and making it a little more easy to understand. So we'll probably do a short webinar on that and also get your feedback. And of course, more event reviews as we have events through the summer. So always check our webinar page. We'll highlight any new scheduled dates at the top of our webpage, and also check social media. So before we get underway, just to show our presenters for tonight, I'm Joe Delicarpini. I'm the Science and Operations Officer here at the Boston office. I've been here since the late 90s, so I've had quite a run here in southern New England. Really enjoy the area and the office. My main job is managing the science program, which includes research and training, so you'll see me on a lot of the event reviews and also these webinars. My co-presenters tonight, first, Bryce Williams, one of our meteorologists. He's been with us just for about almost 2 years now, I think, Bryce, and came to us from the forecast office way out in Spokane, Washington. And Bryce is a native of Tennessee, so he wanted to come to New England to learn about forecasting in a coastal environment, and I think we've pretty much helped him do that. So,
yeah, I'd say so.
All right. Well, Bryce, thank you. And next up is Andrew Lecanto. Andrew, I think it's been, about almost a year? I'm losing track of time, but Andrew came to us from the forecast office in Blacksburg, Virginia, and he's also worked at the forecast office in Burlington, Vermont, and he is a native southern New Englander from the Worcester area. So Andrew came back home, and he's been a great addition to our staff. And of course, Rodney Chai, you may recognize his name from some of our previous webinars. Rodney came to us from the civilian side of the Navy out in Monterey, California, and he's been with us since October and has just really done a fantastic job learning very quickly. He's doing a lot of training right now, but has been really helping lead our event review team. So we really appreciate all his help, and really he's been a great addition to our staff as well. So let's talk about some of the topics we're going to discuss. And most of these are kind of the building blocks, what we call it forecasting. So back in our college days, this was really what we focused on in our first year for meteorology, talking about the atmosphere, weather and climate, global and local circulations, and then things like air masses, radiation balance, which the sun is the driver of our weather, so that's obviously an important topic. Then we'll get into some of the definitions and applications of pressure, wind, temperature, dew point, which you're probably familiar with. Some of the forces that affect air motion. So if you took maybe some high school physics or even college physics, we'll stir up some bad memories for you there. And then we'll talk a little bit about cloud formation and the cloud classification. Clouds are classified as low, middle, and high clouds, so we'll show that. And finally, we'll wrap it all up with a look at fronts and weather maps and show you a little bit of what's happening here today and the next couple of days. So that's all we're going to go through today. So I'm going to lead it off and talk a little bit about the atmosphere. So the atmosphere is divided into different layers, and these are based upon really the temperature structure of the atmosphere. So what you're seeing on this graph are kind of levels here that are split off, but they kind of vary based upon the temperature day to day. So the first layer is the troposphere, and this is actually where all of our weather occurs. It's a very small layer, as you can see, but that's really where all of the weather is contained. Sometimes, a big thunderstorm like shown here can poke up into the stratosphere a little bit, or with a really big winter storm, a strong blizzard, we can get some of the air from the stratosphere to come down into the troposphere, and that really provides a lot of energy. But for the most part, the troposphere is where we focus on as meteorologists. So working up a little bit, we get to the stratosphere, and that level begins where the air temperature becomes isothermal. And what does that mean? Well, this is temperature with height, so it's decreasing through the troposphere. And then here you notice it becomes the same or doesn't change with height. That's called an isothermal layer. So that's where we define the start of the stratosphere. And then you can see it actually warms as you go up. Above that is the mesosphere. Again, air temperature decreases with height. You can see this curve kind of going from right to left. That's decreasing. And that's because there's little ozone way up at these altitudes to absorb ultraviolet radiation. There's more ozone down in the stratosphere, so it actually warms that section. And then the thermosphere, which is the final layer, is separated from the mesosphere by something called the mesopause. And you can see these are all stratopause, tropopause. You may hear us talk about the tropopause when thunderstorms are developing. That's kind of the level where they will kind of just level off, but sometimes they can shoot through. But up in the thermosphere, this is where air temperature again increases because of solar radiation absorption by oxygen molecules. So there's your crash course in the levels of the atmosphere. And just to show you some of the features that you may be more familiar with, obviously our clouds and weather in the troposphere. In the stratosphere, we can get weather balloons to get up that high. Those are the balloons that are launched twice per day around the world, and they sample things like temperature, dew point. They can measure the wind and pressure. And that's all the data that we can look at, and they also go into our computer weather models. Getting up into the mesosphere, that's where the meteors come and burn up. So if you see meteors, you're seeing them come into the mesosphere a lot of the time. Auroras happen up in the lower part of the thermosphere. If you've been up in especially northern New England or even points north, you can see the aurora during the winter. And then up at the top is kind of where the low Earth orbits take place, formerly the Space Shuttle, now the International Space Station. So that gives you a little bit better idea of each of the levels of our atmosphere. So let's talk about weather versus climate. So it's really two different things. So weather is the current state with respect to temperature, humidity, precipitation, visibility, clouds, barometric pressure, kind of just looking at what's happening now. Whereas climate is kind of the prevalent or characteristic weather condition of a place or a region. So a good description I've ever heard is climate is kind of your personality and weather is kind of your mood. So your mood can change day to day, but pretty much your personality will stay the same. So as meteorologists, we really deal with this day-to-day weather. For us at the Boston office, we're looking at the next 7 days. And we're kind of the general practitioners in the weather business. We do everything from severe weather to hurricanes to hydrology to aviation weather, all different aspects of day-to-day weather, whereas climatologists really look at weather that's occurred in the past or is expected to occur in the next 50, 100 plus years. So really two different areas, and we're more specialists in day-to-day weather. So again, these are examples of weather, things like lightning, tornadoes, heavy rain, coastal storms, fog, all day-to-day weather events. And again, it's the condition of the Earth's atmosphere over a brief period of time, usually a day or a week. Now here's a look at climate. And again, this is the average weather over an area for many years. So an example of climate data would be like the normal high and low temperature at Worcester on June 5th, which just happens to be 71 degrees and 53 degrees. But you can see in the United States, this is a map of the Köppen climate classification zones. So each areas that have similar color have similar longer term climates. So for us here in the Northeast, we're more of a temperate continental climate, what's called. And we'll get into some of the things about the air masses in a little bit. But climate is used kind of to split the country into areas that essentially have the same weather over the longer term. So now we'll get into some of the global circulations, and don't let this map or chart frighten you at all. Really just want to kind of show you there are different things that we look at, things like jet streams and highs and lows, and these are all due to the rotation of the Earth. So if the Earth stopped rotating, we'd all be in trouble, but then we wouldn't have all these different weather features either. So the things I want to point out to you on this are a couple of what are called semi-permanent features. One is our subtropical highs, and we don't have a map on here, but this is essentially over the Atlantic Ocean. So this subtropical high in the summertime, like now, for instance, with this hot and humid weather, is typically focused over toward Bermuda, and the circulation around it will pump hot and humid weather up the East Coast. In the wintertime, it tends to shift more to the east toward the Azores, and as a result, we end up getting a little bit cooler. But if you notice, if we ever have like a warm spell in like maybe January or sometime during the winter, it's usually this high is shifted over a little bit more to the west than it typically is. So we come under the influence of that. Now, the other feature I want to show you are these subpolar lows. And these are focused, just south of, obviously, the North Pole, the polar high. But these are what drive our weather primarily in the winter. These are known as you've probably heard the polar vortex. Well, yes, that's what it is. And it's been around for a long time. It's nothing new. And there are a series of these polar vortices, they're called, that are around the globe. And when one of these really dips down into say, the Northeast, that's when we get into our periods of deep freeze or unusually cold weather. For those of you who remember the wonderful winter, I guess, of 2014, 2015 with all the record snowfall in Rhode Island and eastern Mass, we had quite a few of these polar vortices dip down and bring cold air, and at the same time we had the jet stream from the south bringing moisture in, and when those two combine, that's when we get our big winter storm. So really just know that we have a subtropical high that really controls our weather in the summertime, and these subpolar lows or polar vortex that control our weather in the wintertime. So these global circulations really come from heating of the atmosphere. So the sun, again, is our driver of weather. So when things like land heat up, especially say over the tropics, the air rises, it eventually cools and what we call stabilizes, but then has to go somewhere. So it spreads out in either direction, to the right and to the left. The air eventually sinks and cools, and air has to replace what's rising. So you can't have a vacuum. So the air rushes back in, and you get these circulations. And I'll show you in a second how these are important globally. So this is what helps form our jet streams. Again, here's our subtropical high and our polar low. So you can see they help drive the two jet streams, the polar jet stream and the subtropical jet stream. This is our warm and moist source of air, typically in the summertime. This is our colder and drier source of air in the wintertime. But you can see, because of the uneven heating of the Earth, we have more heat in the tropics, obviously, than the poles. So you get these circulations that develop, and it's these circulations that drive not only the low and the high, but our jet streams. So hopefully it's not too confusing, but it really just comes down to heating and the circulation that the Earth is rotating. So you're probably more familiar with this diagram of the jet stream. So our polar jet runs across typically the northern tier of the U.S. This time of the year in the summer, it retreats a little bit more into Canada, and that allows this subtropical jet stream to shift to the north and is more of a driver in our weather this time of year, where what you're seeing on this diagram is more of a winter pattern where the polar jet stream comes down and delivers that cold air. The subtropical jet stream in the warmer air is usually limited to the Gulf Coast or Gulf of Mexico, further to the south. So talking about air masses, these are all classified according to their temperature and moisture characteristics, so essentially where they come from. And they're grouped into 4 categories based on their source region. There's polar, tropical, continental, and maritime. So obviously polar is cold. It originates up in the polar regions of the globe. Tropical, is the opposite. Obviously originates in the warm tropical regions. Continental is over land, and it's pretty much tends to be dry. And then maritime, which makes sense, is ocean, and it has more moisture. So air masses are defined in any kind of combination. A CP would be a cold continental polar, which is a cold, dry air mass. MP is maritime polar, which is cold and moist. And then you have continental tropical, CT, which is a warm and dry air mass, and maritime tropical, which is a warm and moist air mass. So once these air masses form, they can move out of their source regions and obviously bring that kind of weather to other parts of the world. So our example for the winter, you have an Arctic front coming through with a source of cold, dry air behind it. It's not going to be as cold as it is up in the Arctic, but it's certainly going to be colder than what we're used to seeing for this area. And conversely, air coming out of the tropics, we're kind of seeing that this week with the hot and humid weather here in the east. And I'll finish my section with this, talking about these major semi-permanent pressure cells. Again, we have what's called our Bermuda High, which is off the east coast, and this is its summertime position. And then we have some of the polar lows, which can be off of Gulf of Alaska and over off of Greenland, depending on the time of year. But it's these semi-permanent pressure cells that really drive our kind of prevalent weather. And you can see the different sources: maritime tropical, maritime polar, and maritime tropical. So based upon the different weather features, we pretty much know the air mass that's associated with it. This is your hot and humid weather, the maritime tropical. So hopefully I did not confuse you folks too much, but again, if you have a question on anything, feel free to answer it into the chat. And I will pass on our next section, which is energy balance, pressure, and wind, over to Bryce.
Great, thank you, Joe. Great job on that section, and you did not, I don't think you confused anybody too bad. If you did, they can ask us questions afterwards. So hopefully you can ask us a question that you can stump us with. That's what I'm waiting for, one that we can't answer. But we'll see what we have at the end of the presentation. All right, so just to get started on, basically we're going to talk about the differences in heating of the Earth and what that means. So when we think about the weather, a lot of it comes down to the sun. As we know, the sun drives our weather. It creates differences in pressure, which we'll talk about, which creates wind. And so why do we get that wind? Well, it starts with an uneven heating of the Earth. And so one of the major drivers of our weather systems is based on the fact that our Earth is a globe. And so we have a depiction here of the sun on the left, and you have right at the equator, the 0 degree latitude line, we have the sun's rays coming in basically vertically. So that means that more radiation is being received at the surface. You go further up to the poles, up or down to the poles, the rays are hitting at an oblique angle, and so less, more is being bounced off and less is being absorbed. So the equatorial regions are warmer, which everybody, you know already, you learned that in grade school. The tropics are where it's hot, the poles are where it's cold. And so the poles stay colder because of the low sun angle, and the equatorial regions stay warmer. And so the Earth is always trying to find a balance, because there is an unequal amount of warm air in the middle and unequal amount of cold air at the north and the south. And so that causes the air to move around, and we'll talk about why here in a second. So let's go on to the next slide. Another smaller scale feature that would cause differences in heating is just the difference between land and water. So land actually heats up faster and to a higher temperature than water will. It also cools down more quickly and to a lower temperature than water will. And that brings up what we call a sea breeze or land breeze, which I believe Andrew's going to get into later on in the presentation. But this difference in heating isn't just at a global scale. It's really at a mesoscale, because just along the coast, we'll get things like sea breezes setting up because the heat, the land heats up warmer than the water does. And so that's just a couple of the examples for why we get differences in heating. So this is kind of a graphical depiction of that. Some of those oblique rays that you're seeing getting scattered from the atmosphere, absorbed by the atmosphere. This is basically what we refer to as Earth energy balance. So we have solar insolation coming in. About half of the solar insolation, we call it, is absorbed by the Earth's surface. And that is why you'll notice our peak temperature period is usually in the afternoon, late afternoon, because we've had our maximum amount of direct solar insolation, rays being absorbed by the surface and heating up the surface. You have another 20% that are just scattered straight back to the atmosphere by the clouds themselves, and then 19 or 20% that's absorbed by the clouds in the atmosphere as well. Now, those clouds and the scattering and absorbing effect that those clouds can have a big impact on our sensible weather, especially at night. So if you go forward one, I believe that's our next slide. Yes. So this is kind of cool. No pun intended. You'll probably notice on a clear night that it can feel quite a bit cooler outside than it does if it's a cloudy night. And that is because of what is known as radiational cooling when there is no clouds. So you see on the left picture here, that would be a good radiational cooling night because there are no clouds to absorb the energy that is being re-radiated back into space that was absorbed during the day and is being re-radiated. It's going straight back to space. If you go up to look to the very right, you see that energy that is being re-radiated from the Earth is not only being absorbed some by the clouds, but also being reflected back. So it's kind of like a blanket. So you can think of the cloud layer as a blanket at night, keeping the surface warm. So yeah, just something kind of cool with the Earth's energy budget there. So all of this, these differences in heating basically leads to uneven pressure distribution. And so you can see here a global map, just an example of different highs and lows. And you probably have heard of the term somewhere on TV, meteorologists on TV talking about high pressure, low pressure. And we'll get into what those mean later. But for now, just to know that all over the Earth, there's differences from high to low pressure. And what that means, we'll get into now. So pressure, it's, as you know, to put it simply, it's basically the force that the atmosphere is putting on a unit area, or on us, say, at the surface. It's the weight of the air. And you see on the picture on the right, we kind of added a little animation to show just a idea that you see those are supposed to represent molecules. And so you see as you go higher in the atmosphere, there are less and less molecules. So up in, at 30,000 feet, there's going to be less pressure being exerted on these units of air. Whereas down at the surface, you have a lot more molecules above you. And so that's inherently going to be heavier and you're going to have higher pressure. So the higher we go into the atmosphere, the lower the pressure is. Now, I kind of, one example I like to describe or show when I'm in person is if you think of it as like a milk carton, a tall milk carton full of milk, and you poke a bunch of holes in it all at once from top to bottom, the holes at the bottom are going to have the milk shooting out farther away from the carton than the holes at the top. And that's because there's more milk above those holes. So there's more pressure being exerted on that section. So it's similar in the atmosphere, less pressure above, more below. All right, moving on. Just some cool statistics for you statistical, nerds like us that really dislike this kind of stuff. The highest ever pressure that was ever recorded was 186 millibars, and the lowest that it's ever been recorded was 870 millibars. Excuse me, and that's not including tornadoes. Generally, just some thresholds here. A Category 1 hurricane, you could think of around 980. Category 3 hurricane, around 950. And we'll explain what those categories mean if you come to our Tropical 101 forecast or webinar later. All right, so all that leads to the wind, which everybody knows what the wind is. It's just air moving across the Earth. And so how we predict wind and really know what it's going to do is we look at those pressure areas. So we know that wind flows from high to low pressure. So you can go forward here, and the magnitude of that is determined by the gradient of that pressure change. So this is just an example showing these black lines. They're called isobars. They're lines of constant pressure. And the wind is going to be strongest where the isobars are more compact. That's where the gradient is strongest. A example I like to describe for this to show how the wind moves faster where the gradient is tighter. If you imagine a big trampoline with lots of marbles ringing around the outside, and I was to place my finger right in the middle of the trampoline, the marbles on the very outside are going to start slowly moving in because the gradient or the change in height of that surface is less. Whereas if you had marbles really close in to the middle of the trampoline, I put my finger there, they're going to rush in really quick because that's where the change is steepest. The gradient is steepest. Similar to wind, where the gradient is steepest, you're going to have the fastest velocities of wind. So when we think of hurricanes, they have hurricanes and storms that create a lot of wind. We think of tight pressure gradients. So the pressure gradient force is one force that acts on the wind. Another force that we talk about is called the Coriolis force. And this may be a little less familiar to some of you. This is basically an inertial force acting on all objects that are in motion relative to the Earth, or a rotating reference frame. So it's a little hard to describe, but easier if you look at the graphical depiction. So you're looking at the top right graphic of the globe. Imagine there's a plane that's moving, where the red arrow is moving from up in Canada down to Florida. If it's going in a straight line in absolute space, going in a straight line, well, the Earth is rotating all the time, right? So it is going to appear to curve. And so this is what Coriolis force is. It causes moving objects like planes and birds to deflect to the right of their motion in our hemisphere. Another example you see here with the record player. You can see if you start a pencil and you move it along a ruler, so it's straight in an absolute sense, but the record is turning as you go. That line that you're drawing is going to look curved. That's the same idea as Coriolis force. Now, how this plays into the weather is this provides a lot of the spin for our atmosphere. This is what provides the spin for hurricanes. And now, with regard to hurricanes, the Coriolis force is actually strongest at the poles and goes down to 0 at the equator. And so that's why you will really never see hurricanes form within, about 5 degrees latitude of the equator. And there's never been a hurricane that has crossed the equator after it's formed. So, the hurricanes really need that spin to survive, and it's 0 at zero latitude. Now, there's a third force that also acts on the wind, and all these together are what creates the motion. So that's called friction, and you probably have heard of that in reference to just a basic science physics class. It's what, if you slide a book across a desk, that's what's going to keep it from just going off into infinity. It's the force that causes anything to slow down. But with weather, it's the force that causes the air to slow down too, as it spirals into lows and out of highs. So low pressure, basically with the frictional force, the pressure gradient force, and the Coriolis force all combined, we get this idea that you see on the top right, where the wind will spiral counterclockwise in the northern hemisphere into a low pressure and spiral out of a high pressure clockwise. And so as it does this, say in low pressure, it's spiraling in, and that's causing a convergence at the center. That's causing, the air's got nowhere else to go. It can't go underground, so it's going to go up. That's why we get clouds over low pressures. And high pressures, you have air evacuating from the center. That's leaving a space, and so air is dropping then above it to fill that space. And that's causing what's known as subsidence, sinking air, and that dries out the air and keeps the skies usually cloud-free under high pressure. So that's why low pressure is associated with cloudy, stormy days, and high pressure is typically associated with sunny and nice weather. And I think that's it for me, and we'll be on to Andrew.
Okay, so we'll go ahead and we'll talk about temperature. I think will be in the next slide, and there it is. So delving a little deeper into temperature. Temperature is at its basic level is just the sort of the degree of hotness or coldness of an object, or for the purposes of us in the weather business, it's the air, how hot or cold the air is. But if you really delve down deep into it, it's actually a measure of the average kinetic energy or the speed of the air molecules. And you can see that depicted there in the graphic there. We have sort of high temperature, the molecules are moving really quickly, versus at a lower temperature, the molecules are moving a lot slower. And that's sort of the scientific measure of temperature, is again how quickly are those molecules moving. And basically, the more kinetic energy the molecules have, the higher the temperature, and vice versa. So a lower temperature means they're not moving as quickly as they were if the temperature was really high. And we sort of measure the air temperature with a thermometer, such as pictured there on the far right. And there's three measures that we can use to express temperature. One is the Kelvin scale, and that's one that's not typically used to report the air temperature, but it's for scientific purposes. It's convenient for scientific calculations, but for most of the world, air temperature is expressed in Celsius. But in the United States, we refer to temperature as Fahrenheit. And there's conversions that we can use to go back and forth between the different units of temperature. Next slide. Okay, now moving on to dew point, and that's a measure of the moisture content in the atmosphere. And sort of more specifically, it's sort of like the stickiness of the air. If you've been outside today, you certainly have felt the stickiness outside, and that's just because our dew points are so high. And by that, our current dew points right now are in the mid 60s to 70 degrees Fahrenheit. And so a lot of times we hear when you talk about just how humid it is outside, many people will refer to the humidity, but it's the dew point that actually is sort of the measure of how sort of muggy and sticky the air is. And the dew point itself, defined is the temperature at which air has to be cooled for saturation to occur. And when we call saturation, what happens there is that condensation happens, and you get things like fog, frost if the temperature is cold enough, and you get dew. I'm sure many of you have seen in the morning have had some dew the last few nights is because their dew point's been really high. And higher dew point temperatures just indicate there's more water vapor in the air, which indicates that the air is just moist. Next slide. Okay, now we're going to move on to the vertical component of wind. And many of us, obviously we live on the ground, and most of us just think of the wind as being the horizontal movement of air. But air actually moves in all three directions, and while basically this vertical element of the wind it's not as large as the horizontal one, but the one exception is with thunderstorms, and what we have what sort of the wind component with those are what's called updrafts, and that's pictured here on the picture on the right, where basically you have differences in air between warmer air at the ground, and that eventually what happens is if that air is forced to lift, what happens it'll cool and condense into clouds, and they'll tend to build vertically. And what we see typically is that the vertical component for wind for thunderstorms can be significant, but in many other instances the vertical element of the wind is really not too substantial. And then air that's, as I mentioned, air that's rising and cool. Moving back to so that's just an element there, that vertical component. What that will do is that'll just help to facilitate cooling air as it rises. Next slide. Okay, so Bryce alluded to this earlier. This is what we call the sea breeze, and at night the land breeze. And the way that works is basically as Bryce alluded to before, is that the land and the water will basically they'll warm at different rates, and in fact the water tends to be a little more temperate. So what you have is you have a difference in temperature between the hotter land and the cooler water during the day. So what you have is you have this circulation that flows from the water to the land, basically to try to cool off that temperature difference. And that air will rise and it'll condense and it'll circulate back and forth, just like as I'm drawing here. So that leads to the sea breeze, and we'll see that during the day, especially along the east and southern coasts of southern New England. Especially the last few days, we've seen the sea breeze that'll develop, and that'll help to sort of cool off the near shore areas. Sort of the opposite effect happens at night, where we have what's called the land breeze. In other words, what happens there is basically that temperature change is reversed. In other words, the land cools off at a quicker rate than the water does. So you have this circulation that develops, and the wind flows from the land to the water, and it just circulates, through the upper parts of the atmosphere back to the ground. So that's called the land breeze, where the winds blow from the land to the water. Next slide. All right, so now moving on to cloud formation, and that is basically cloud forms. The clouds form when air rises, cools, and condenses. Rising motion can be associated with convection if the air is unstable, or you can also get it through lifting of air over mountains, or topography is sort of a general term for that. And you can also get clouds and rising motion through lifting of air through fronts. And we'll talk more about fronts here in a little bit. But that's sort of some processes that we can use to get rising motion, to get air to rise, cool, and then condense into clouds. And as air rises, the temperature of a piece of air, what it'll do is it'll cool, and eventually it'll reach its dew point temperature, and then you start to see sort of a cloud element start to form as it becomes what we call saturated at that point in time. So condensation occurs, and then the water vapor in the air condenses into those tiny water droplets, and you see that in the shape of a cloud. And as you see here, the condensation nuclei are basically what that can be things like it could be salt, it can be air pollution even, that can help sort of nucleate some of that water molecules. In other words, basically it'll sort of congeal to it. And as you see, the water molecules are really, really small compared to the size of a condensation nuclei, which is also fairly small, but the water molecules themselves are also really small. Next slide. All right, moving on to the classification of clouds. And there's three ways that we can classify clouds. There's the height, high, middle, they're low clouds, or if they're vertically developing clouds. We can also classify them by their physical appearance. If they're wispy, if they look like cauliflower, there's that sort of physical appearance that can also use to classify clouds. And then there's this third one, which is whether or not they produce precipitation, because not all clouds do. And here are a few sort of Latin roots that basically will help when it comes to identifying cloud types. And several clouds will sort of follow these Latin roots. So the first one is called cirro, and that cirro means high, or sort of like a curl of hair. The next one is alto, which is middle. Stratus is a layer or like a sheet-like sort of appearance. Cumulus, and that's the sort of those heap-like cauliflower puffy-looking clouds. And then there's nimbus, and those clouds produce precipitation. So those are those Latin roots that'll sort of help you to come up with the cloud types. Next slide. So the next slide we have here is going to be on the different types of high clouds, and there's several high clouds that we do have. And see what's listed here is there's cirrus clouds, and then there's cirrocumulus clouds, and there's cirrostratus clouds. And those clouds are high clouds in the atmosphere that are they're mainly above 20,000 feet. And those clouds are they're thinner, they're white in appearance, and they tend to have again, they're sort of wispy looking, and they're also composed of ice because they're so high in the cloud. They're so high in the sky, so the temperature that they're associated with is usually really cold and will entirely support ice. And again, these clouds are typically very thin. They can sometimes, if they're low on the horizon, they can display a really an array of different colors. And some of those are pictured here. Next slide. So the next type of clouds are mid-level clouds, or mid-clouds. And those typically, those have bases that are between 6,500 feet and 20,000 feet. And those clouds, again, they sort of reside in the middle part of the atmosphere. And those, but they're obviously they're a little bit lower in the sky compared to high clouds. So these clouds tend to be composed of water, but they can, depending on the season, they can also be composed of ice crystals as well. And the two mid-level clouds that we typically see are the altocumulus clouds, and those clouds tend to look just like little puffballs, versus the altostratus clouds, and those clouds tend to be flatter. Again, we mentioned stratus as one of those Latin terms. It tends to be a little bit more like a sheet or like a layer. So you could see that sort of distinction between the two types of mid-level clouds there. Next slide. And then moving on, we've got low clouds. Those are bases that typically are below 6,500 feet. They're obviously located in the lower part of the atmosphere, and because of that, they're mostly composed of water droplets. And there's 3 or 4 different types of low clouds. There's the stratus clouds. Again, those stratus is that was really sort of again, that blanket sort of appearance. There's stratocumulus, which those are lower clouds that look a little puffier, have a little bit of vertical development, but not too much. And then there's cumulus clouds that are those are more of a cotton ball sort of appearance. And then the one at the bottom is cumulonimbus, and those type of clouds, the cumulonimbus clouds, those are your thunderstorms. They tend to have they can actually span multiple layers, and we'll talk about that in a second. But if the temperatures are low enough, while most of these clouds are mostly composed of water, if it's cold enough, they can contain snow or ice particles, again, if the temperatures are cold enough. Next slide. All right, so we'll also talk about the vertically developed clouds. Again, we sort of alluded to one. This is the cumulonimbus. Those tend to span an entire depth of, though they can span the entire depth of the troposphere. But some basically cumulus and cumulonimbus clouds, those can sometimes vary in terms of how deep they can be. So these type of clouds can contain both liquid droplets and ice particles, just because they can span that larger range of depths in the atmosphere, especially in the troposphere. And under the right conditions, cumulus clouds can become powerful thunderstorms and called cumulonimbus clouds. Next slide. All right, that'll end my portion of the webinar. So what I'll do is I'll pass it on to Rodney. We'll talk more about fog.
Well, thank you, Andrew. The guys have done a great job in laying the groundwork for my section. So, and at the very end, we're going to do some applications to the current weather, and we're going to use the tools to diagnose the current weather. But let's talk about fog first. And as Andrew has alluded to, we have experienced fog over the past few nights, especially at the coastal areas, and sometimes into the river valleys as well. And usually in early summer, when for our area, when the ocean temperature is still cold, you have warmer air being blown over cold ocean waters, and that leads to fog development. And usually when you get a southerly wind you can get the fog to kind of come up against the South Coast as well as the Cape and Islands. And last night, Boston actually got soaked in fog, which made for some very nice pictures. And that was because of the more of like a easterly flow, and that fog, the marine layer, kind of was pushed against Boston. And so coastal areas, you can have, we call them the marine layer, and that's when it's associated with a front that's called advection fog. And for people living in the Connecticut River Valley, you might be more familiar with radiation fog and valley fog. Radiation fog is pretty much when you have the temperature fall at night to the dew point temperature, and when you get 100% relative humidity, you get fog and kind of misty conditions. And sometimes the fog may be dense as well. And then the fourth one is upslope fog. That's more for mountainous areas, like the Rocky Mountains out west. And then you can also get sea smoke or steam fog. Those could be hazardous for mariners and boaters, and we'll cover that in the marine weather webinar. And then we can also get precipitation fog, and that happens when you have relatively cold raindrops falling on warm ground, and you can get those kind of like steamy conditions after a heavy downpour. So that's about fog. So let's talk about fronts and weather observations. Next slide, please. And one way to think about fronts is that it's, Bryce, Joe, and Andrew has talked about how we have differential heating from the sun across different surfaces, and you get the land being able to gain or lose heat faster than the water. And front is basically, it's kind of like a transition zone or boundary between two air masses. And so an air mass could be colder and drier, and then you have the other air mass which is more moist and warm. And in the summer, that when we get cold fronts, like we're going to get one tomorrow, kind of approaching our area, you don't necessarily get a decrease in temperature, but you would kind of experience a low reduction in humidity. And but in the winter, when you can get Arctic fronts, and sometimes those may be preceded by snow squalls, which we had a few in this past winter. You can get dramatic drop in temperature, like just like 30 degrees, like in a few hours. And to summarize, there are 4 types of fronts that we're going to talk about. Next slide. We're going to start with the warm front, and as the name suggests, this is warmer air replacing cooler air. And usually the warm front will come up from the south, and when this happens, and remember, warmer air is less dense than colder air. So you can visualize you have a cold air mass sitting in our vicinity, and you have warmer air which is less dense. So it's going to lift itself above the colder air. And as it does so, it leads to formation of clouds. And usually this favors widespread continuous precipitation. For snow lovers, if you look at the surface map in winter, usually you have, you kind of like a setup when you have the cold, dry air in place, and then you have the warm front trying to lift north. And if the cold air mass is cold enough, then it's going to stay all snow. But if the cold air mass is not cold enough, then you can get transition into mixed precipitation and those freezing rain and sleet. But we're going to talk about that in Winter 101. But to recognize warm front, just know it's warm, so it's red color, and you have those ovals kind of ahead of the line. So that's a warm front. Next slide. The opposite of a warm front is a cold front. So in this case, the colder air replaces the warmer air. Now remember that the colder air is more dense than warmer air, so it's going to sink. So when you have a warm air mass in place and a cold front approaches, it's actually going to lift the warmer air above itself. And as that happens, and when you have instability in place, you can get towering cumulonimbus clouds. Like we have seen a few times this late spring, early summer. You might remember the severe wind event we had on May 15 and June 6, and that was kind of preceded by some very photogenic shower clouds, and that's the leading edge of the thunderstorms and the cold front behind it. And we're going to talk about this in the Severe Weather 101, so stay tuned. But just as a primer, when you have a cold front, it provides a lifting mechanism in an unstable air mass. So you have air rises, and then it leads to formation of clouds. And sometimes this cloud can shoot into the stratosphere, and that's what we call overshooting cloud tops. Cold fronts are demarcated by a blue line with triangles. So that's how you recognize them on surface maps. Next slide, please. A stationary front is when the air mass, the warm air mass and cold air mass are relatively similar in strength. So you don't get, neither is able to dislodge each other. But stationary fronts tend to be transient or temporary in nature. Eventually, one side is going to win out. And so an example would be, let's say you have a cold front, it sweeps through southern New England, and it clears the coast, but then it kind of loses strength, and then it kind of stalls and becomes a stationary front. And eventually it may lift back northwards as a warm front. So to recognize a stationary front on surface maps, you look for the red ovals and blue triangles on opposite sides of each other, so to kind of represent a stalemate. But then again, this is transient in nature and usually doesn't last long. Finally, we have the occluded front. And the reason why you can get occluded front is because the cold front typically moves faster than the warm front. And a key concept to remember is, so when Bryce talked about low pressure, weather fronts are usually associated with low pressure, because low pressure, you have rising motion and typically stormy weather, whereas high pressure, you have sinking air and stable weather. So, and remember, low pressure rotates counterclockwise because of the Coriolis force in the northern hemisphere. In the southern hemisphere, it's the opposite. So when you get the counterclockwise rotation, and typically you get the warm front out ahead of the cold front. And an example would be, right before the arrival of a cold front, especially in the fall and spring, you might feel it's going to, it gets very warm and muggy. And that's because the warm front has lifted north. But that's really just out ahead of the cold front that is lurking behind. And sometimes this cold front catches up with the warm front. And when that happens, that becomes an occluded front. And on the weather map, we represent the occluded front with purple color, which is the combination of blue and red. And we put the circles and triangles on the same side. So that's not to be confused with stationary front, which they are on opposite sides. So next slide. So putting it all together, let's take a look at the current weather, or the weather that happened a few hours ago. So this was a surface observations map from about just before 3 p.m. And you can see that the red colors is wind gusts. Black color represents temperature, and dew points are in blue. And no wonder it is so muggy, because the dew points are in the mid 60s to low 70s, so feeling very tropical out there. And see, the higher temperatures are located in the Connecticut River Valley and towards the Merrimack Valley in northeast Massachusetts. Usually when you have a setup like this, northeast Massachusetts tends to do better in temperature than southern Massachusetts and Rhode Island, because you get the downsloping effect. And when the air sinks, it warms. So you have the low 90s in northeast Massachusetts and the Connecticut River Valley. Whereas along the south coast, you will see temperatures are only in the 70s, and Nantucket is only in the 60s. That's because of the clouds and the sea breeze coming off the ocean, and the ocean right now is still in the upper 60s, so it's going to bring a chill to the air. And during heat waves, people like to go to the Cape and the South Coast to cool off, and I don't blame them. But we see, the southerly flow is pretty strong, with winds gusting up to almost 25 miles per hour in some locations. So, that's the temperature and that's the wind. So just by looking at the wind direction, we kind of can have like a pretty good first guess what is happening. But in order to further diagnose the weather, we need to look at a more regional scale. So next slide, please. And this is a surface analysis pulled from the Storm Prediction Center website. And for people who like severe weather, you might be familiar with the SPC website, and you might eagerly await their severe weather outlook. And this is something we're going to cover in Severe Weather 101. But they also do produce very neat, what we call meta-analysis maps. And in this case, the lines that you see are lines of constant pressure, or isobars. And what we typically want to see on a map like this is, where is the low pressure located? Because low pressure is associated with fronts and areas of storminess. So we see a 998 millibar low pressure located over the Great Lakes. And sure enough, you can see an area of precipitation. It's almost like a line of storms kind of stretching down from the Great Lakes southwards into the Ohio River Valley. And on the back side of it, you have another swap of precipitation. It's kind of like lake effect rain. So in winter, there would be lake effect snow. So the fronts are not drawn on this map, so you will have to use your imagination a little bit. But a clue usually to locate the fronts is the wind direction. So out ahead of the low pressure, the winds are from the south. But notice how far north it goes. So the warm front is located somewhere in Canada, so it's probably out of this map. But where is the cold front? You look for an area where there's a change in wind direction, and that's kind of located between Ohio and Pennsylvania. You see the wind out ahead of the cold front from the south, and the winds behind the cold front from the west. And the line of storms is kind of out ahead of the cold front, because the cold front provides a sort of lifting mechanism for the cloudiness and storminess. And that cold front is going to come our way sometime tomorrow, midday into the afternoon hours. Next slide, please. And a tool that we like to use as forecasters is satellite imagery. And this is something we're going to talk about more in our radar and satellite interpretation course. And what you're seeing here is really a composite product. So you have the satellite imagery showing the clouds. And in this case, it's called the day cloud phase product. And the clouds are colored. So the bright colors, in this case, the orange color, are the high top clouds, typically associated with ice crystals and thunderstorms. And what you are also seeing is are those detected lightning strikes in the clouds. So it's kind of like they're embedded in the orange clouds, which makes sense because those are the towering cumulonimbus. And in this map, the pressure is also overlaid on the map, so you can kind of see the low pressure kind of rotating over Michigan and Lake Huron, and you can kind of make up the cyclonic curvature to the low pressure, or the counterclockwise flow. So out ahead of it, you have the southerly flow and storms firing away, and then on the back side of it is the colder air, and as the colder air kind of makes it over the Great Lakes, that gives rise to lake effect clouds and showers. And those are typically lower top clouds. And you can see in the day cloud phase product, it is in blue and green color. And for us, we don't have any fronts affecting our area today. So those pop-up thunderstorms that you see in the Green Mountains and White Mountains, those are just from differential heating between the land and the ocean. And but once that cold front passes or approaches our area tomorrow, we're going to see a line of possibly strong storms with strong wind gusts from 12 p.m. onwards. So you would want to stay weather aware, especially tomorrow afternoon. So next slide. So looking ahead, this is just a loop of the forecast surface maps going out to the next 3 days. And you can see the cold front clearing our area. And then after that, Thursday is looking dry and less humid. So for those of you who want a break from humidity, Thursday would be your day for outdoor activities. So next slide. So just a recap of what we talked about. It's been a long, and we very much appreciate you for listening to this Weather 101 class. And if you have any questions, be sure to ask them at the end. So right now, I'll just pass it back to Joe. And thank you again for listening.
All right. Thanks, Rodney. And thank you, everybody, for your attention. I know this is probably a little bit longer than we normally do, but we wanted to include kind of as much as we could just for a basic Weather 101 class. So maybe what we'll do is we'll take the about next 10 minutes. We don't want to keep you too long and go through some of these questions that we received. So Rodney, Andrew, and Bryce, you can certainly help me answer these. So first one's from Catherine. Is the NAO a type of circulation? I understand the NAO can affect New England winter weather. I can probably answer that one, guys. It's known as a North Atlantic oscillation, and we'll definitely address this in our winter weather course. So it's essentially the difference in pressure between kind of Greenland and over toward the Azores. So when it goes negative, that's when we tend to see the colder and stormier weather here in the Northeast. And when it goes positive, we get the opposite. So, for example, this past winter was fairly mild with a lack of snow, and that really featured a positive NAO for most of the winter. Whereas when we had the winter of 2014 and 15 with the record-setting snow for 6 weeks, we were really stuck in a persistent negative NAO pattern. So, yes, it is a type of circulation, and we will definitely get into that for Winter Weather 101 in the fall, Catherine. Great question. Question from Jared. Did the severe reduction in flights during COVID-19 change any information flow with regard to weather forecasting? I can answer that one too, guys. Yeah, it did in a way. So a lot of the aircraft are equipped with sensors that measure temperature, pressure, wind, kind of like the weather balloons, but obviously we get them going across the globe. So there was a definite decrease in the amount of data we had from the aircraft, especially over the Pacific, where we need more data because we just don't have, obviously, the weather balloons being launched from the ocean. That's the way our weather goes west to east. So that's typically where we like to have the aircraft data. So there was definitely a lack of that. Did it really impact the quality of the data? The jury's kind of out on that. But I'm sure to some degree it did have, at least a minimal effect on maybe the accuracy of the model. So good question. And, now the flights are slowly coming back. So we should have a little bit more data as we go through the summer and the fall. A question from Samuel. Why is it so sticky outside when it gets really warm? Bryce, I'll give you that one.
Yeah, thanks, Joe. I'm on my iPad and I can't see the questions. So yeah, if you can just
I'll read them to you.
keep reading them out, then that works. So yeah, so why is it sticky out? Well, basically because the air or the water droplets are condensing onto your skin because the dew point is so high. So basically the dew point, the higher it gets and the closer to the actual temperature it gets, that means the closer to saturation. So basically the air is getting closer to saturation. And so instead of you being able to say when you sweat, for that air to that water to evaporate off your skin, the air is so thick and close to saturation that it's not, those droplets aren't able to evaporate. So the sweat will stay on your skin, and just the air in general feels like it's condensing on you. So yeah, the higher the dew points, when we start to get up those dew points up here, in the upper 60s, we're getting in the 70s, that's when it's starting to feel oppressively humid and sticky out.
All right. Next question from John. What factors cause lower high pressure systems to weaken or strengthen? Bryce, you want that one too?
Sure. So it depends. When we're thinking of, say, hurricanes, big areas of low pressure, those are strengthened because of the fuel that they run on, which is basically the warm water, the warm air coming up off the water. So with those low pressure systems, the warmer the air and the stronger the air is rising into the atmosphere and forming clouds, the more fuel it's got, the stronger it's going to get. And then as it either, for one, reaches land, it encounters not only friction, but it also loses its source of fuel. So it's energy, because it doesn't have the warm water to feed off of. It can also encounter what's known as wind shear, which is different directions of winds with height that basically tears it apart. So with hurricanes, you have that. Basically, the intensity of the heating or the cooling and the discrepancy between what we call differential heating. So the difference between the hot and the cold, that's going to cause, that in itself is going to cause these systems to be stronger or weaker. And basically the storm can outrun its life cycle, its fuel that it's running on, and then just kind of peter out as it encounters areas of more friction, and also moved into areas that are less favorable for storms, areas that are drier, areas that are cooler, things like that.
Okay. And also for our winter storms, John, if we have really warm ocean temperatures, that helps because you have a much bigger difference between the colder air coming in from Canada and the warmer air over the ocean. So that it's really a difference in temperature that drives, whether a low or a high will be weaker or stronger. Good question. Okay, Allison has a dew point question. My weather app says humidity 61%, but doesn't say dew point. What is the difference, and should I get a different weather app? Ooh, who wants that one? Andrew?
Yeah, Allison, that's a good question. So the humidity expresses a percentage. That's think of that sort of like a ratio of how basically how close to saturation the air is. I mean that depends on the temperature. Basically, warmer temperatures can hold more water vapor than colder temperatures can. So what you'll see is that for the same dew point is that the humidity would be lower if the temperature was really high. So it's the dew point that's really the measure of sort of how sticky and how humid the air is, and that's basically an actual measure of how much water vapor is actually in the air, not humidity itself. So that's sort of an important distinction between the two, as the dew point is sort of the absolute measure of how much water vapor is in the air versus humidity, which is it's actually referred to as relative humidity because it depends on the temperature. It depends on how warm or how cold the air is. That'll determine the humidity of the air. Should you get a different weather app? That's a great question. It's nothing I can endorse, but some weather apps will show humidity and dew point. But should you get a different one, that's entirely up to you. But that's probably how I would best address that question. But that was a great question, though.
Okay, good. Let's see, another question from John. How far inland is the climate impacted by the sea breeze? I can answer this one. It kind of depends on the weather situation, but on a typical day, the sea breeze on the eastern Mass coast can get out to at least like the Route 128 corridor, if not 495. And on the south coast, typically gets into like south central Connecticut through a little bit north of Providence and into southeast Mass as well. I've seen it some days make it all the way in past Hartford and Connecticut and up to Worcester, Mass. So just depends on the strength of it, and that strength is really defined by the difference in temperature between the ocean and the land. I've seen other days where it's been pretty weak and barely makes it to like Logan Airport in eastern Mass and barely onto the south coast. So good question, but it kind of just varies day to day. Typically, you'll get further inland in the spring when the land heats up quite a bit and the ocean's still cold. But this time of year, we're into the summer now. I would say probably in eastern Mass, somewhere between 128 and 495. And then on the south coast, probably somewhere like central Connecticut, north of Providence, and then toward maybe Taunton and Mansfield, kind of in that area. So good question. Let's move on to a few more. And don't want to keep you folks too long. Question from Jim. This could be a good one for Bryce. He's our cloud guy. What causes the sky to be orange, red in the evening or in early morning? There's a saying that red sky at night, sailors delight. Red sky in the morning, sailor take warning. Why is that, and what causes that?
Oh, great question. And hopefully I'm right on this, and Joe or Andrew, Rodney, y'all can correct me. But I'm pretty sure it's because so at night, if the basically the red skies at night is supposed to be inferring that you have cirrus on the back of the storm, that's the left, and red skies in the morning means that the cirrus is ahead of the warm front. So that means that the clouds are going to be lowering through the day ahead of an incoming storm system. But honestly, I've never looked into it. So I'm going to defer to, somebody else to say.
Back to me.
Am I on track?
Yeah, it's an old rule of, a lot of rules of thumb that work very well. But yeah, that's pretty much it, Bryce. It has to do, essentially in the morning, you're looking at advancing cirrus or altocumulus, which means the clouds are coming in, the moisture is lowering in the atmosphere. So usually by the afternoon or evening, you'd be having rain or snow.
That's what I thought, because usually, because ahead of the warm front, the clouds are typically higher, starting as a cirrus, and then they'll get lower and lower.
Exactly. And Jim, I'll have to apologize because Bryce is from Tennessee, so he's from a landlocked area. So
exactly.
I should have taken that one.
Plead the fifth.
All right, we've got one more question. This is from Dan. This is a good one, and maybe I'll let each of us answer this quickly. What's the next big thing that will advance your forecasting abilities in the next 10 years? I'll answer that one last. Let's start off with Rodney on this one. What do you think, Rodney? Next 10 years, what's the next big thing that will advance our forecasting ability?
Yeah, that's a great question. I think, it's a combination of our satellite technology, and as you saw when we did the weather diagnosis. We saw how the satellite image enhance our ability to understand or diagnose the atmosphere. And in an example, in severe weather days, we have 1 minute satellite imagery. It's almost like looking at radar, but you're looking from top down, and so that's one aspect of enhancing weather forecasting. And the other aspect would be, I would say, we are really getting very good in high resolution models, and not just that, but we are also getting very good in looking at ensemble forecasting. And so, one way to think of a weather model is, you look at people who love snow, who would like to look at the GFS and the Euro, but you're looking at deterministic output. But nowadays, there's an emphasis on looking at the ensemble members and seeing how many members agree with a certain solution. And if you have high level of agreement, that gives you more confidence in the forecast. So yeah, I would say between satellite technology and high-res ensemble forecasting.
All right, so we got to vote for satellites and models. Okay, what do you think, Andrew?
Yeah, really, Rodney sort of took the words right out of the wind out of my sails, because I would say I would certainly the satellite and model, certainly for sure. I guess the other one would be advances in radar technology. We've seen, I guess that's maybe a little different than what Rodney was talking about. So I guess that's my just advances in radar. There's I believe there's something coming out soon called phased array, or within the next several years to decade. And I think that'll go a long way to sort of in addition to radar. But that's several more years down the road. So at least in the very short term, certainly the new advances in satellite imagery. We've just got the GO 16 satellite. That's been tremendous for. I think I speak for most of us. It's been tremendous for us. But also, weather models keep getting better and better. They're still not perfect, but they are definitely getting better. And those, I think, all three of those go a long way towards sort of helping us out.
All right, similar. And Bryce, you got any comments?
Yeah, I won't wax eloquently because they kind of covered a lot of it. But I would say one thing that I hear a lot about in the research field is machine learning and like artificial intelligence type stuff that I would think would really move the computer modeling part of compiling all that data that we get from satellite and radars, and actually being able to advance how well we can predict the atmosphere. And probably I would say in the next 10 years, I would guess that advances in that machine learning, that type of thing would allow us to get maybe the accuracy that we've got now with days 3 to 7, maybe be able to achieve days 7 to 10, even just increasing our accuracy in the longer range, I think, probably.
All right. Yeah, and I'll just throw my 2 cents in real quick. I agree. I think, Bryce, the computing has been will be much even better than it is now. And I would say just the past 5 to 10 years, the leaps and bounds we've made with computer technology has been tremendous, just from what I've seen. And I think that artificial intelligence will come into play where we're doing things like the model will have all sorts of data from past weather events, 40, 50 years, and we'll forecast things based upon that information. We'll kind of know, kind of like an analog, what the most likely outcome is. So, really good
totally.
question, Dan. Wow, that was a good one, and actually from everybody. Thank you very much.
Made us think.
All right. So I just want to thank again everybody for attending. I will let you know this has been our most attended webinar that we've held so far. So thank you so much. And I know it ran a little bit long, but we wanted to get to everybody's question. Again, this is recorded, so it will be on our YouTube page once Bryce puts it up there in a day or two. And again, thank you for joining. Please send me your feedback. My email address is there, or you can respond to your webinar confirmation. Let me know what you like, what you don't like. This was kind of a basic Weather 101, and I know some folks may have thought it was a little bit too basic, but we really don't want to get too technical on these 101 presentations. We'll do a little bit more in our Weather 202 coming a little bit later in the summer. So don't worry about that. We really want to reach out to kind of everybody in the area, so to help everybody understand weather a little bit more and help us share kind of what we love to do day in and day out, forecasting and everything else here in Southern New England at our National Weather Service office. So once again, I want to thank Bryce and Andrew and Rodney for joining me, and I want to thank all of you for joining us on our webinar. Please join us for future webinars, and you can find those on our webpage, weather.gov/Boston. There is a headline up at the top that will take you to our webinar page. And once again, thank you. Have a good night, and we'll talk to you soon. Take care.
Thanks, everybody, for listening. Good night.
Thanks, everybody, for joining us.